Sometimes in this game you get to do an interview where you can genuinely say, the person I'm about to interview needs no introduction. This is one of those occasions, but if I were to do that, it would wreck the fun of getting to introduce the interview, and why would I deprive myself of that? So this episode we are interviewing Lord Martin Rees, the Astronomer Royal. Martin Rees is one of the foremost cosmologists and astrophysicists of our time. He was made the Astronomer Royal in 1995, has been the Master of Trinity College, Cambridge, President of the Royal Society. He's written more than 500 research papers across various areas of astrophysics and cosmology, including contributions to the origin of the cosmic microwave background radiation, the final proofs of the Big Bang theory through studying quasars, and gamma-ray bursts. In the latter part of his career, he has been an immensely influential populariser of science, writing books on cosmology such as Just Six Numbers and Our Cosmic Habitat. And he has also devoted himself to considering grand problems of the future of humanity and the existential risks that we face. His book, Our Final Century, helped to kick off the field of existential risk studies, and he co-founded the Centre for the Study of Existential Risks at the University of Cambridge in 2012. It is no exaggeration to say that a great many of the ideas that we've discussed on this show, and my own personal inspiration to study physics in the first place, owes to the work of Lord Rees both in discovering much of the science in the first place, and then again in popularising and explaining the ideas so wonderfully in his books. I was extremely grateful that he was willing to be so generous with his time and respond to such a large range of my questions. Our interview touches on existential risks, the current pandemic, extraterrestrial life, cosmology in general and the history of cosmology, and the nature of fundamental physics and what is still left to find out. Without further ado then, the interview. First of all, Lord Rees, I want to thank you very much for being so generous with your time and coming on the show today. And we'd like to start by talking about the field of catastrophic risks. So in 2003, you published this book, Our Final Century, which helped to kick off a flurry of academic activity in this field. And you co-founded the Centre for the Study of Existential Risks a few years ago. Similar organisations have sprung up all over the place. Reflecting on this effort to get people to take these risks seriously, have you had the impact that you've hoped so far?
Well, ironically, the COVID-19 pandemic has made us more relevant and people take these serious global threats more seriously. But the history is that I've always realized that this century is special. It's the first when one species, namely the human species, has the power and number to actually affect the whole world. We're collectively changing the world's climate and its biodiversity by our actions, and also we are able, through our technology, to cause runaway catastrophes. And so things are special this century. And as you say, in my book in 2003, I addressed this question. And I have a more recent book, which is called On the Future Prospects for Humanity. And the main point is that we do need to worry about the dangers which we can cause by error or by design. And of course, the COVID-19 pandemic is an event which does have global consequences. And that's a wake-up call, as it were, and makes us aware that we do need to plan and be prepared for a new class of catastrophe, which couldn't have happened in a less empowered and less interconnected world.
At the time when you wrote Our Final Century, you had a rough estimate of the odds of making it to the end of the century at around 50-50. So I wanted to start with a sort of optimistic approach and said, let's say we make it to the end of the century. What did we get right? And therefore, what do we still need to do?
Well, I think we will have a bumpy ride through this century. I think one can imagine that we could have wiped ourselves out, but I think that's pretty unlikely. But I think events worse than the present pandemic are almost certain to occur during this century. And also there's a new class of threats from, for instance, cyber attacks, which knock down the electricity grids in a whole country, or bio threats, engineered pandemics rather than natural ones. So I think there's a growing range of things we need to worry about. So we'd be very lucky if we get to the end of the century without having had a fairly bumpy ride. That's all I would say. But I wouldn't want to put any sort of firm probabilities on these things. All I would say is that there's a very important maxim that the unfamiliar is not the same as the improbable. And of course, we've never had a pandemic quite like the present one. Um, and there are other possible dangers that may emerge, which are so serious that one occurrence is too many, and we need to prepare for them. And I think one thing that has been learnt in the last year is that we ought to think a bit more in advance about these scenarios so that we are better prepared for them.
Coming on to the COVID-19 pandemic then, so when I ask about the impact of it, I'm sort of reminded of the old historian's joke when asked about the legacy of the French Revolution. Please ask me in a few hundred years. You had this famous wager that there would be a mass casualty event from bioterror or bioerror by the end of this year. Now, COVID is a natural pandemic, but it's not dissimilar to the kind of catastrophe that you warned of and envisioned. Reflecting on it, it feels like some parts of our response held up better than we expected, while others were much worse. So I want to ask, given that you'd thought about this in advance, do you think this pandemic has unfolded as you expected? And what has and hasn't surprised you about how we've responded to it?
Well, I hadn't thought through a scenario of what the response would be. And I have to say, I was thinking already of some not natural but engineered pandemic, because I was very worried when I read that back in 2011, two research groups had been able to modify the influenza virus to make it more virulent and more transmissible. And of course, if that can be done with some viruses, simple ones, then it won't be very long before it can be done with things like the coronavirus. So I'd been thinking that the first real global pandemic would be an engineered one. I know there's some people who think that this pandemic started with a leakage from the lab. I don't think many people think that's correct, so they think it's a natural one. But we were, I think, prepared for an influenza pandemic because there had been bird flu and things like that in the past. But what we weren't prepared for at all were the special features of a coronavirus. In particular, the fact that we would be unlikely to quickly get a vaccine against it, and also that it would require protective clothing, etc., because of the way it was transmitted. And so we were not prepared in those two respects. And this is, in a way, surprising because there had been two similar types of virus, SARS and MERS, in Asia within the last 20 years. So we couldn't say it was a very improbable event. And incidentally, perhaps it's because there had been these precursors in Asia that the countries of East Asia handle the present pandemic far better than we have.
Yes, I think that's certainly the case. And one thing that I think is interesting is in many of your works, when you talked about the threat of a pandemic, you would say that there would be a potential for society to collapse or for anarchy to happen if hospitals became filled.
Yes.
And I don't think that any of us really anticipated this sort of level of social restriction being possible or able to be implemented by governments. In some ways, I think we've actually shown that we can act collectively when there is a problem like this that arises, at least within societies. But then internationally, the response doesn't seem to have held up very well. And it seems like each country is going their own way. I mean, do you think that's a fair assessment? And do you think, reflecting on this and how it might relate to other catastrophic risks, there are ways that we should shore up our defences against things like this happening in the future?
Yes, indeed. I think we need to be on a wartime level of preparation, in a sense, to cope with these things properly. And the countries which were most successful were, of course, those that were most draconian in their early lockdowns, etc. And we and other European countries were less successful than those in the Far East. And I think we do need to be prepared, and the public need to be prepared for such events, so that it doesn't come as a shock, and we don't have to sort of think things out on the fly, as it were, when the disaster comes.
The pandemic has brought the idea of science policy and the phrase we all hear a lot of, following the science, into the limelight, for better or worse. I wondered if you'd like to talk about your experience in the House of Lords and discussions with politicians that you've had perhaps before this about these catastrophic threats, and also the role that science should or shouldn't play in policymaking.
Yes. Well, of course, it's clear that in the case of this pandemic, the scientists have been learning as they went along. There were lots of things that were quite unclear back in March, which are now clearer. And of course, when the facts change, then policy changes. And so it's not surprising that there have been changes in policy. But I think the public tends to feel that the scientists do, in effect, know the answers and it's clear what should be done. But that's not the case. And of course, even when the scientists can give clear information about the scientific aspects of a phenomenon, then politicians have to take that into account, but along with other things like the economic and the social and political consequences of the action. And so science is part of the decision making, but it's not the sole determinant of what actually happens. And scientists should realize that there are other factors that politicians have to take into account where scientists aren't experts and where they're just concerned citizens. So that's one point. But there are sometimes cases when the scientists are not prepared and don't know what advice to give. Perhaps I can give two examples. One was back about 30 years ago, mad cow disease. It was a very unusual kind of disease which surprised everyone. And at first it was thought that it would not be transmitted to humans, and then it was. And it was so uncertain that one had no idea how serious it would be. In fact, about 100 people died from mad cow disease over a quite long period. But if you'd been the science advisor to the government back then and you'd been asked, is there a 1% chance of 1,000,000 deaths? You'd have to have said yes. It couldn't be ruled out. And so the politicians, therefore, would be justified in overreacting. And to take another very different case, the unpronounceable Icelandic volcano, which exploded a few years ago, you may remember that.
Yes, Eyjafjallajökull or whatever it was.
Right.
I tried.
Say it again.
Eyjafjallajökull, something like that.
Yes.
I apologise to any Icelandic listeners we may have.
Yes. Well, this was an example where advice was actually an overreaction because there'd been no sort of preparation. Everyone knew that there were explosions of volcanoes in Iceland, etc. But what they did was they stopped all flights in Northern Europe. What they would have needed to do, really, to be better prepared, would be to know better how resilient jet engines are to different kinds of dust and whether the warranty governing the aero engines would still apply, and also have better ways of tracking where the dust actually was.
Mm-hmm.
If a similar eruption happened now, then the reaction would be less extreme because they would know what was dangerous and what was not. Whereas because they didn't know, the reaction was overcautious and excessive. And so one reason for doing scenarios in advance is not only to be prepared when things happen, but not to overreact when things happen.
I mean, it's an interesting balance between reaction and overreaction. I think those of us who were worried about existential threats before, thanks to warnings like yours, I feel like we took the pandemic perhaps a little more seriously earlier on, as we were motivated by a sense of the fragility of our civilization. And I think now everyone can see that modern humans, our technology has not made us immune from these catastrophic risks, and we can all see the price of the disruption that they can cause. And I wonder if the long-term response to this pandemic will be that if a virus emerges in the future, people will take it much, much more seriously, much more early on, and attempt to nip it in the bud, where we have that maximum kind of leverage of action to act early on. And you would also hope that our societies in the future would devote more resources to thinking about these problems and trying to work out the most effective ways of being prepared, rather than dealing with the rather large expense of trying to deal with the problem after it's already got out of hand.
Well, certainly to some extent, because estimates of the total cost of this pandemic in money, let alone in lives, are something like £20 trillion. And if you work out the insurance premium by multiplying the cost of an event by its likelihood, then even if you thought this would only happen once every 50 years, it would have been worth spending a few £100 billion in preparation. We didn't.
I'm thinking of people like Florian Kramer here, who suggested the idea that you might want to come up with vaccines against the diseases that were most likely to cross over into humanity, even if they haven't done so yet.
Oh,
This
yes.
would be an effort that would cost some billions of dollars, but
That's precisely the kind of thing we should do. We should try to be prepared and have the expertise so we can quickly have a virus. And of course, politicians need to realize that they may have to sanction the spending of money that may turn out to be wasted if the pandemic doesn't occur. And back in 2009, I think some politicians were criticized rather unfairly because they stocked up on vaccines against a flu pandemic that didn't occur. To criticize politicians for taking that precaution that was unnecessary is as unfair as criticizing someone for taking out fire insurance when their house doesn't burn down. And so we've got to accept that some preparations will lead to unnecessary expenditure. But I think to be on the safe side, we are going to need to be prepared more. And of course, this is the case for studying diseases in greater detail so that we can work out how transmissible they are, etc. And of course, let's not forget that pandemics are only one class of extreme risk we need to worry about.
So this is a recurring theme in your work, really, which is about the perils of short-term thinking, businessmen who want short-term profits, politicians and democratic establishments that are too concerned about the politics of the next election. What do you think we can do to encourage longer-term thinking and planning? Do we need a cultural shift?
Well, I think we do. Of course, let's take the issue of climate change. Um, that's really, in a sense, a slow motion version of what we've had to deal with now. Now we've had a crisis that we have to respond to very quickly. In the case of climate change, we can predict with great confidence that conditions will get very serious, at least in the second half of the century, and that we can prevent these serious consequences only if we change our course now and do something to reduce our dependence on carbon. But it's very hard to persuade people to devote resources to something when the benefits will accrue 20 or 30 years from now, and moreover, will accrue not to your own nation, but to people in remote parts of the world, which will be more affected by climate change. So it's very hard to get politicians to take account of these long-term threats unless the public does, because the politicians won't do it if they lose votes by spending money in a way that the public doesn't support. So I think what we need to do to promote long-term thinking is to go directly to the public. It's not enough for science advisors to tell politicians what may happen in 30 or 40 years. The politicians need to have this concern fed into their inboxes and see it in the press and realize the public's concerned. And so what's very important is that the public should be aware of the downside of climate change and think ahead. Most people do care about the life chances of their grandchildren, and babies born today will still be alive in the 22nd century. So it shouldn't be too difficult to persuade people that they should care about what might happen 50 years from now, even though the standard economic discount rate, which would apply to putting up an office building or something, would attenuate your concerns after about 2050. So we need to think long term. And I think here, religions can help. In fact, the papal encyclical in 2015 called Laudato Si, where the Pope talked about our obligation to the non-human world and the climate and the environment, etc. That was very influential. He got a standing ovation at the UN, and he has a billion followers in Latin America, Africa, and East Asia. And the fact that politicians knew those followers cared made it easier to get a consensus at the Paris Climate Conference in December 2015. And a smaller version we had in this country a couple of years ago, which was when Mr. Michael Gove, not perhaps the most enlightened politician, introduced legislation to ban non-reusable plastic drinking straws and things of that kind. Now, the reason he was prepared to do that was he knew that the voters would support him. And the reason the voters would support him is that our secular Pope David Attenborough, as it were, had fronted those TV programs Blue Planet 2, which showed, among other things, an albatross returned to its nest and coughing up for its young, not the longed-for nourishment, but bits of plastic. And that had made the public aware that accumulation of plastics in the ocean was an environmental concern.
I think it's interesting, this parallel with religion, because, once religion did provide a sense of something beyond ourselves and beyond our own lives, which, as you write about in your books, inspired people to build cathedrals that they knew they would never see completed. Do you think that contemplating the long-term future of our species of intelligent life could provide the same motivation today for secular people? And would that be a reason for us to continue speculating on these subjects?
Well, I think so. It's true that we do need to think long term, because the one thing we do know is that our world has billions of years ahead of it. It's taken 4 billion years or thereabouts for our biosphere and us to evolve from simple beginnings in the young Earth. But we know that the Earth will last for 5 or 6 billion years more before the sun flares up and dies. So we're not even the halfway stage in the life of our planet. And so we certainly think longer term. And of course, it's at first sight paradoxical that we don't think long term, to the extent that the cathedral builders did when they were happy to build an edifice which wouldn't be finished in their lifetime, but which still inspires us many centuries ahead. But I think the reason for that apparent paradox is that things are changing so fast. The cathedral builders, they thought maybe the world would end in 1,000 years, but at the same time, they thought their children and their grandchildren would live lives rather like their own, and therefore they would appreciate the finished cathedral. Whereas now, things are changing so fast, I don't think we can, with the same confidence, say what life will be like for people 50 years from now. And I think that uncertainty is an excuse, as it were, for not thinking long term, because we're not quite sure of what people want then, what the issues will be. So we need to do our best to uh, try and foresee what will happen, and of course ensure that innovation is responsible and that we avoid uh, developing the kind of technologies which will be damaging in the long run. But it is very hard to get people to think long term when it's clear that things are changing very fast.
Mm-hmm. It almost causes us to discount the future because it's so
Well,
uncertain,
that's
or
right.
because
We,
we're so
we need
uncertain of
to
what we might want in
apply a
it.
low discount rate to these things, but because of uncertainty, as you say, we do discount it too much. And we've got to realize that irreversible damage can be done if we don't, for instance, try to control our CO2 emissions.
I would feel bad if I got through this whole conversation without having at least one question about extraterrestrial life. We can see in recent years that the astronomical parameters that are relevant to trying to work out the probability of life, things like how many exoplanets there are, what their atmospheres might be
Mm.
like, are being narrowed down by new studies
Mm.
now. Others, like the likelihood for life to develop initially or for life to become intelligent once it started, these things remain elusive because we have just the one data point here on Earth. How do you think astrobiology has shed light on what we might
Yes.
expect? And what would you view as the best prospects for finding
Yes.
evidence of life?
Well, I think you've given a very good summary of what is becoming more certain and what's still very uncertain. The big, exciting development, of course, in the last 20 years in astronomy has been realizing that most stars are orbited by retinues of planets, just as the Sun is orbited by the Earth and the other familiar planets, and that there are in our Milky Way galaxy many, many millions of planets rather like the young Earth, about the size of the Earth, orbiting a star rather like the Sun, at a distance where water could exist, neither boiling away nor being frozen all the time. And so those are all candidates for life. But what we don't yet know is how likely it is that life evolved, because we don't know how it began on Earth. We understand Darwinian evolution, how simple life evolved by natural selection into the biosphere that we are part of today. But the transition from complex chemistry to the first metabolizing, reproducing entities that we call alive, that is still a mystery. And that's a fascinating question, even to the most earthbound biologist. And so I hope that we'll make progress in the next 10 or 20 years in two ways. One is we might understand the origin of life because more people are now working on that problem from a terrestrial perspective, but also we will perhaps have evidence from data gained by the next generation of even bigger telescopes we now have for whether any of these planets orbiting nearby stars have any kind of biosphere, because there are spectroscopic signatures of chlorophyll and oxygen, etc. And so if you've got a strong enough signal, which implies a very, very large optical mirror, then you might be able to take a spectrum and get an inference of some sort of biosphere around some of these planets. And that's something which will be feasible with the next generation of telescopes. In particular, there's a telescope being built in Chile by the European Southern Observatory. It's a consortium of astronomers in Europe, which we belong to in the UK. Unfortunately, Brexit doesn't stop us belonging to that. And this will have a 39-meter diameter mirror, and this will collect enough light from planets orbiting nearby stars to be able to get at least a crude spectrum from them. And this will be the first way we can perhaps, if we're lucky, find evidence for life. And of course, the other thing that would be important would be to look more carefully in our own solar system. Of course, Mars may have some evidence for life there, we don't know, but other places in our solar system, like the moons of Saturn and Jupiter. There's Enceladus, a moon of Saturn, which has an ocean with water underneath, and Europa, which is a moon of Jupiter, which also has a frozen surface with water underneath. And it could be that there's something swimming in those oceans. And within 10 or 20 years, probes will be sent to look for that. And even if it's very simple life, then finding evidence for it elsewhere in our solar system, particularly in the outer solar system, would be crucially important, because if it turned out that life had originated twice independently within our solar system, that immediately says it's not a rare fluke that's happened on Earth, and therefore it would have happened on a large fraction of the other Earth-like planets. So finding evidence for life on Enceladus or Europa would immediately say that there's likely to be life in literally millions of places in our galaxy. I'm cautious about mentioning Mars because some people point out that it might be possible for life to be transmitted between Mars and the Earth by meteorites, etc. So it could be, in a sense, we're all Martians and the life came from Mars to the Earth. But I think it would not be so likely that it could be transmitted from as far away as Jupiter or Saturn to the Earth. So that would have to be independent.
The philosophical implications of that for things like the Fermi paradox and trying to understand what else is out there would be truly profound. So you think that these things, these atmospheric detections, are far more likely than some of the other things people have suggested, such as finding radio waves via SETI or seeing big astroengineering projects out there in space where which advanced civilizations might have
Well,
built?
I think so. It's obviously less likely that to be intelligent life or technological life than some life of any kind. And indeed, biologists who study evolution on the Earth, they debate about whether the emergence of intelligence was fairly automatic, or whether if you were to rerun the clock on the Earth, you might end up with a very different set of flora and fauna on the Earth today without intelligence. So people wonder about how many contingencies had to be fulfilled for intelligent life to arise on the Earth, even once it had got started as simple life. So we don't know. But my take on this is that we don't know. But if we were to detect some artifact or some manifestly artificial transmission, it would probably come not from a sort of civilization rather like we have on Earth today, trying to send messages to us, but it will be from something electronic. And let me explain why I say this. If you look at the history of life on Earth, then it's taken 3 or 4 billion years to get from the simplest life to us. And for a few thousand years, we've had a sort of technological civilization. And it may be that within the next 1,000 years, this will be usurped by some sort of post-human electronic civilization. If that happens, then those electronic entities may be near immortal. They may not want to be on a planet. They may prefer zero G. They won't need an atmosphere, so they will go off into the blue yonder. So in the far future, there may be electronic entities which are, in a sense, our progeny, but they're not flesh and blood. And they will exist for billions of years, perhaps, even though the flesh and blood civilization that created them may only exist for a few thousand years. Now, if there was another planet where evolution had gone roughly the same way as on Earth, then of course it wouldn't be synchronized. It would be most unlikely that it would be synchronized within a few thousand years when the ages of the stars differ by billions of years. So if it had lagged behind, then of course we see no intelligence, whereas if it had been a billion or even a few million years ahead of us and along the same track, then of course it would have got far beyond the stage when it would be a flesh and blood civilization, and so any evidence of it would be in these electronic entities left behind. So my prediction is that may not find any evidence for civilization, but if we do, it'll be something electronic, which will be some artifact left by some long dead civilization. And of course, we then confront, as you mentioned, the Fermi paradox. This is the issue of whether it's surprising that we haven't already been invaded, as it were, by intelligences from elsewhere. The argument there is that some planets will have had a 1 billion or 2 billion year head start over the Earth because they're around older stars. So why haven't some of them got to us before we got to them if the origin of intelligent life is common? It's a good argument, obviously, but I think there are many escape clauses. I think the most important one is that post-human evolution is not governed by Darwinian selection. It will be what I call secular intelligent design. It will be us designing machines of superhuman capability, and maybe the machines then designing still more themselves. And so since it will be some sort of design, not just random process like Darwinian evolution, then it's not going to necessarily have the qualities needed for success in Darwinian competition. Darwinian selection favors intelligence, but it also favors aggression. But this future evolution, which is technologically led, may not favor aggression. And so it could be that there are super intelligents out there who are living an entirely contemplative life and showing no expansionist tendencies and not revealing themselves. So this is really a case when absence of evidence isn't evidence of absence.
It's interesting because there's this estivation hypothesis that maybe they are out there waiting for the universe to be cold enough to make it worthwhile to do their calculations.
Well, that's another reason why they might not be conspicuous now. Yes.
I also wonder if maybe it is the fact that the civilizations that remain aggressive don't actually make it past the filter that we're approaching at the moment, and that only the ones that are able to direct their evolution in a more benign way actually do survive.
That's certainly another possibility, because it could be that we will perhaps survive the next century, but not much beyond that, and not for long enough to have allowed our post-human progeny to get beyond the Earth.
So this is also a physics podcast, and I really wanted to talk about cosmology for a little bit. I think the fact that we can infer so much about the nature of our universe, its history, and its future essentially just from the starlight that falls on our planet in experiments that we've performed on Earth. It stands out for me as one of the greatest stories that we're able to tell. Our understanding of the cosmos has evolved hugely over the course of your career, and you contributed a lot to some of that. Would you like to talk about what it was like when you first got involved, cosmology, and some of the subsequent developments that you think have been the most important and the most surprising, perhaps?
Well, I do think that when the history of science is written, what's happened in cosmology in the last 50 years will be one of the most exciting chapters, because it has really transformed our understanding. If you go back just 50 years, um, no one knew whether our universe started with a big bang or not. I mean, my senior professor, Fred Hoyle, when I was a student, he believes in a so-called steady state universe, which was expanding, but it went on forever. And as the galaxies dispersed, new ones formed in the gaps, as it were. So it never started from a big bang. And that was a controversy, and we didn't know very much about the overall scale of the universe. Whereas since that time, we have learnt through very compelling lines of evidence that everything started in a hot, dense beginning, what we call the Big Bang, and we can trace properties of the material back to within a billionth of a second of the very beginning of all. As we trace things further back, then everything would have got hotter and denser near the beginning. And the reason the first nanosecond is a mystery is that every particle then has higher energies than we can achieve even in a big accelerator like the LHC at CERN. So we can't understand the physics of the crucial tiny initial instant which happened. But after that, we can understand what happened, and we have fossils of different stages. We have very good evidence of what happened when the universe was a few seconds old. That's when helium, deuterium, and hydrogen uh, underwent nuclear reactions and emerged in certain proportions. And when we look at the radiation which fills space, microwaves, they are a relic of the hot, dense beginning. The radiation was very hot and dense, but as the universe expanded, the universe cooled down this radiation and diluted it, but it's still there and it's observed in microwaves. And this was discovered in the late 1960s. The other thing that we've learned is that this early universe was not completely smooth. It had some fluctuations in it, some places where the density was above average, somewhere density was below average. In the places where density was above average, as the universe expanded, they'd be decelerated more by their own gravity than the average, and they would eventually condense out into bound systems. And that's, crudely speaking, how galaxies formed. And so we know that the universe started hot and dense. We know by studying the background radiation that it had these fluctuations. And moreover, we now know from computer simulations that those fluctuations had the properties needed to give rise to galaxies of the kind that we observe now, grouped together in clusters in the way we observe now. So we have a pretty good outline picture of what happened in the 13.8 billion years since this Big Bang. But, of course, every advance brings into focus a new set of problems. What we would like to know is, why is the universe expanding the way it is? Why does it contain the amount of atoms and radiation it does, plus also some other particles that make the so-called dark matter? And why does it expand in a smooth way, except for small fluctuations? The answers to all those questions lie in this first tiny fraction of a second, which is still rather mysterious. Mysterious because the conditions are so extreme, we don't yet understand the physics. And so that's a challenge for the future, to try and get clues to the physics that prevailed at these very early stages, which are conditions too extreme for us to do direct experiments. So that is the challenge now, and to understand what happened in the Big Bang. Was our Big Bang the only one? And how big is the universe? How much further does it extend beyond the range of the telescopes we can use today? And I should have said that most of the progress has been due to not armchair theorists, but to observers using more powerful telescopes, and also telescopes in space able to observe X-rays, infrared, ultraviolet, etc. And that's allowed us to observe um, galaxies um, and other objects out to very great distances. And of course, we have an advantage over geologists and paleontologists in that we can actually see the past, because when we look at distant galaxies, we're seeing them as they were when they were younger, and we can look back far enough to see galaxies when they were newly formed. And so we can check our theories by seeing, do they match the way galaxies are today? Do they match the way they were 1 billion, 2 billion, 3 billion, 4 billion years ago, etc.? So we have quite a number of good checks on whether our theories are basically correct. So obviously we can't be certain, we may be missing some crucial features, but we do have a much clearer picture now of our galaxy, our place within it, and the physical laws that govern it. And the other thing we've learned is that Einstein's theory of gravity does seem to be correct. We had no good test of this 50 years ago, whereas now we find evidence for black holes, which are the most extreme and fascinating predictions of Einstein's theory. We could study them in detail. So we've made tremendous progress in understanding the physical laws which govern stars, black holes, and galaxies, and most of the Big Bang. That's a rather long answer to your question, I'm afraid.
No, that's a wonderful overview of cosmology. You know, it's so interesting. I'm writing a series of episodes at the moment covering the history of cosmology, and I tried to think, where should I begin with this story? And the place I ended up beginning was Fred Hoyle on what is now Radio 4, I suppose, addressing people saying that most of the theories of cosmology had been worked out and that it was in fact the steady
That's
state
right.
theory, because that was the moment that he coined the term
That's
the
right.
Big Bang in an almost slightly derogatory
Yes.
way. At the start of your career, that was a very active debate between the steady state universe and the Big Bang Theory, which you helped to resolve. For my generation, I think when I look at cosmology from a historical perspective, the thing we have to appreciate is that all of these things take on an aura of inevitability once we know about them. You know, the narrative of the Big Bang is established for
Yes.
us, and so it almost seems natural to say that the universe had a beginning because we've always taken this as an assumption. But the actual process of inferring what's really going on from astronomical observations, when you have several different theories that could explain them, is a lot trickier. I mean, would you like to talk a little bit about your experiences being involved in that debate between the steady
Yes.
state universe and the idea that the universe had
Yes.
a beginning?
Well, of course, the idea of a Big Bang was first clearly formulated in the 1920s by Lemaitre, who's a Belgian priest, and he was the first person. He called it a primordial atom, and this was an idea, but there was no way of testing it. And there were two things which happened in the 1960s. The first, which was one that happened in Cambridge, which I followed closely, was that uh, the radio astronomers, led by Martin Rees, they discovered that some galaxies emitted very strong radio waves. We now know that the radio waves are energized by black holes in their centers. But what Martin Rees realized was that some of these things were a long way away, uh, even further away than the optical telescopes could probe at that time. And Martin Rees surveyed the sky and compared the relative numbers of apparently bright and apparently faint ones. And he showed that the number of faint ones was surprisingly high compared to the number of bright ones. And that implied that there were, as it were, more a long way away than there were closer by, as compared to if they were in Euclidean space. He interpreted this as saying that they were a phenomenon that was more common when the universe was young than today. Turns out he was right, because young galaxies are more prone to have these outbursts than the present day ones. But of course, that was inconsistent with the steady state theory, uh, which would have said that at all eras, on average, things look the same. So this was the first tentative evidence, but it wasn't completely compelling. There were some ways around it. And what was far more compelling and made most people take the Big Bang seriously was the discovery that intergalactic space was filled with weak microwaves, seemingly coming from all directions and having no obvious source, and realizing that this radiation was best explained as the afterglow of the hot, dense beginning, the radiation that was hot and dense and became diffuse and cool to 3 degrees above absolute zero by the expansion. And this discovery made most people accept the Big Bang. Fred Hoyle never really did. He still wanted to have a more complicated idea. He ended up with a sort of compromise, which I would call a steady bang, but he never really reconciled himself to the standard hot Big Bang. Although, ironically, he did some of the best work underlying the theory. I mean, I mentioned earlier that we can predict what proportions of hydrogen, helium, and deuterium would be made in the Big Bang as it cooled down to temperatures of a few billion degrees. And he and colleagues did some of the best calculations on this. And his great achievement, which did survive, was realizing that, contrary to what Lemaitre had thought, the rest of the periodic table, carbon, oxygen, and iron, and all the elements that we're made of, couldn't be made in the Big Bang. Only hydrogen, helium, and deuterium, and a bit of lithium. He realized that most of the elements which we're made of were synthesized in stars. And the idea here is that stars get their fuel by nuclear fusion. They get most of their energy by turning hydrogen to helium, but then they turn helium into carbon, then to oxygen, and up to iron. When stars end their lives, the heavy ones explode and fling back into space this processed material, and this material then condenses into a new generation of stars. And so, according to this wonderful story, our solar system condensed about 4.5 billion years ago from a gas cloud already contaminated by the debris from earlier generations of massive stars which had lived and died and thrown back processed material into stellar space, including carbon, oxygen, and all those elements. So we now know that every atom of carbon in our bodies is made inside a star, and that we actually have inside us atoms which had their origin in many hundreds of stars spread through the Milky Way, stars which lived and died at least 4.5 billion years ago, so that their debris was part of what formed our solar system. And that's a wonderful story which Hoyle and his collaborators actually outlined back in the 1950s, and that has survived. So Hoyle was a really great figure in this subject.
In recent years, ideas about the multiverse have gained a following in both popular and serious science, and you were one of the people who initially supported and suggested this. One advantage, at least philosophically, is that a multiverse might help to solve this anthropic fine-tuning problem of why the universe appears to be so well calibrated for complexity and human life. I wondered if you'd like to talk first on your thoughts on this fine-tuning problem and the parameters that appear to be tuned to allow us to exist, and whether we need a multiverse to help us resolve this.
Yes. Well, fine-tuning, it's the point is that you can easily imagine a sort of counterfactual universe which would not allow complexity in life. I mean, for instance, if the properties of atomic nuclei were such that you didn't get nuclear energy, you'd have no chemistry. You'd just have a universe of just hydrogen. Or if gravity was very strong, then stars might exist, but they'd be very small and short-lived, etc. So it's clear that there have to be parameters in some particular range in order to stand a chance of having complexity. You want a lot of time, and you want stable stars, etc. And it's easy to imagine a counterfactual universe where that didn't happen. Just how much fine-tuning is needed is a bit controversial, but you certainly need some. But quite apart from that, there are some theories of the very early universe which go under the name of the inflationary universe ideas, which are mainly put forward as an explanation of why the universe is expanding the way it is, and why it's more or less the same on average everywhere we look. It turns out we have a problem. Why, if we look in all directions out to 10 or more billion light years, the universe looks the same. How did it homogenize in this way? And the idea of the inflationary universe, which was put forward nearly 40 years ago, is an idea which is a rather compelling explanation of this. It's not battle tested as a theory because it's hard to directly test it, but it's a very good idea. Moreover, some versions of this have the property that you would get many big bangs. You'd have a sort of substratum which is expanding exponentially, and big bangs will condense out of it, not just one but many. And the main advocate of this is a Russian cosmologist called Andrei Linde, who works at Stanford. He had a theory called eternal inflation, which involves the idea of many big bangs. And there are other versions like this. And then, of course, the second question, if there are many big bangs, would they all be governed by the same physical laws? Or might it be that the physical laws and constants of nature are different in different ones? So that, as you say, some could be tuned for life and some not. And here we don't know, but there are some theorists, particle physicists, who believe in string theory, who think that there could indeed be many different forms of empty space, many different vacua, in each of which the microphysics could be different. So one possibility, the most exciting idea, is that there are many big bangs, and as each one cools down, it's governed by different microphysics from the others, and therefore some will be more propitious for emergent complexity than others. But there'll always be some which will be tuned so that life can exist. So that's a speculative idea. But the idea of inflation is a popular interpretation of why the universe is so uniform on the large scale. And there is a debate among particle physicists about whether the laws of nature are unique or whether there could be other possible laws of nature in other kinds of space. So these are on the frontiers, and of course, one is hopeful that these problems will be settled in the next 50 years. I'm not all that optimistic about all of them because the simple things have been done, and when you get to these things which are harder to test, then of course it may be a longer wait. For instance, the Higgs particle was predicted in the 1960s. It was 50 years before the evidence for that was found in the LHC accelerator at CERN. And so it could be that we'll have to wait a long time before we have evidence for theories which allow us to address these questions about the very early universe. We don't know. And of course, to be slightly more philosophical, it's also possible that there could be a theory like superstring theory, which is a unified um, uh, theory that brings together gravity and Einstein's theory, which is a dominant force on a large scale, with the forces in the microworld. There may be such a unified theory, but even if it exists, it'll be too hard for us to actually understand. No particular reason to think that all the key features of nature are accessible to human minds any more than Newton's ideas are accessible to a monkey. And so it could be that we will hit the buffers, and that even though there is a theory, we won't understand this. And then, of course, you might ask the other question, will AI help us? And it's quite possible that there are theories like superstring theory, which involve very complicated geometry in 10 dimensions. And there are lots of variants of these theories, and it may be just too difficult for a human being to actually work through these very complicated concepts and this complicated geometry. But through the advantage of speed, an AI may be able to do this. And so it could be that we will only know if a particular unified theory is correct because it's been fed into an AI and the AI has done the work and has spewed out at the end of its calculation the correct strength of gravity and other important numbers about the universe. That may be one way to go. But I think we're going to depend on better instruments in the lab and in space and better computers. And already we depend very much on computer powers to simulate what happens in space because we can't do experiments crashing black holes together or crashing galaxies together in the way that particle physics crash particles together. But we can, in the world of our computer, do just those things. We can ask what would happen if two galaxies crash together, if two black holes merge, etc. And then we can compare the results of those calculations with what we actually see when we look out into space. And that's the way we get a feel for whether our theories are on the right lines, whether the simulations which we can do are a good match for what we actually see in the sky. And that's a very important technique in astronomy, where we can't obviously do direct experiments but can just observe.
It's fascinating. Just coming to this sort of question of the end of theoretical physics, and or rather, I suppose, when we look at the history of how physics has developed, there's this interplay between theorists and experimentalists. Sometimes theorists lead and come up with testable predictions, which are then falsified by experiment. Sometimes experimentalists lead and find unexplained phenomena which need theories to be modified in order to adapt them. There's often this interplay between the two. As you point out, in particle physics and in this fundamental high energy physics, we're reaching the point where we can't really probe those higher energies anymore. And we're getting to the stage where we're confirming things like the Higgs boson, which was first theorized some years ago. And it seems the theorists have advanced a long way past the experimentalists, at least for the field of high energy physics. But one of the passages from your writing that really stuck with me the most was the point that a full understanding of our universe really goes beyond where reductionism can take us. I think there's this tempting idea in physics that you can just reduce everything down to these fundamental physical laws, and that the main challenge we're trying to solve here is to write those down. And then once you have them, you can just say, well, I have the Schrodinger equation, which describes the atom, and humans are made up of atoms, so of course I can basically derive all of the complex phenomenon just from these fundamental equations. You can almost see the textbook saying that, the universe is left as an exercise to the reader. But it makes you think that perhaps what's left in a lot of physics is taking different approaches to understand different phenomenon that are occurring in the world and make predictions. I mean, do you think that there may be more room in other areas of science as opposed to sort of endlessly chasing this fundamental theory?
Well, I'd like to put a gloss on what you said. The phrase theory of everything is often used, and that's a very misleading and hubristic term to use, because it is true that we aspire to have a theory that does tie together the four fundamental forces of nature, maybe string theory, maybe something quite different. But of course, that would give us a fundamental understanding, but it wouldn't actually help most scientists with their work. I mean, if you're a chemist, still more if you're a biologist, you're not held up to not understanding enough subnuclear physics. You're held up because you're dealing with very complicated things. And so one point which I try to make in my book is that the sciences are in a sort of hierarchy where each one has its own irreducible concepts. So if you're a chemist, you talk about valency and things, and if you're a biologist, you talk about cells or maybe organisms, etc. Or higher up the, the chain, you may talk about systems and sociology, etc. So every science has its own concepts, and it's a valency in chemistry, perhaps, and it's imprinting in animal behavior, etc. Let me give you a simple example of the sense in which the reductionism does and doesn't occur. Let's take a subject like fluid mechanics and fluid flow, which is a sort of serious academic subject, and you can understand when flows go turbulent and what happens when you get a breaking wave and things like that. Okay, and this is a serious subject, and people who work on this subject, they don't care at all that water is H2O. They treat it as a continuous fluid, and they use concepts like turbulence and viscosity, which are emergent properties, and they can calculate when things go turbulent and etc. And it's a predictive science. But having said that, they wouldn't deny a breaking wave is a solution to Schrodinger's equation. If you could solve Schrodinger's equation for 10 to the 30 atoms, then this would be a solution. No one's denying that. You're not saying there's anything sort of mysterious about a breaking wave. But the main point is that even though one is reductionist in the sense that one believes that these things are solutions to Schrodinger's equations, that's not a way to understand them. It wouldn't give you any enlightenment if you could do some monster computer program and end up breaking wave at the end. We understand it in terms of the concepts of fluid mechanics. And I use that example because no one thinks anything mysterious about the way water flows. But if we go higher up the hierarchy to living things, of course, some people in the past thought there was something special, vitalism, etc., which entered living things and made reductionism even less credible. But my view is that in principle it's just the same, just as in the case of the breaking wave and the water flow. It is a solution of Schrodinger's equation, but just even in the case of the water flow, it's pretty useless to try and solve Schrodinger's equation. That is even more the case for something as complicated as a living thing.
You might be able to write down the Hamiltonian for a human being, but you won't be able to predict what they'll say to you next.
We have to write it down because if we involve about 10 to 30 particles, we can't. But the point is that even if you compute this, it wouldn't give you the insight we want. And the human beings, the insight is in terms of emotions and all that. Just as for a chemist, it's not subnuclear physics that matters.
So as our understanding improves, we're kind of pushing up against the limits of what we can know, as we've sort of touched on here. In cosmological terms, we're pretty confident we can predict what the universe was like a billionth of a second after it began, and trillions of years into the future as well. But let's say you could ask some omniscient being anything. Is there a major open question in cosmology or in science more generally that you would love to have an answer to? And if so, do you think there would be a prospect for us to answer it?
Well, I mean, I think the very beginning of our universe, where the conditions are so extreme that we clearly need some unified theory of gravity and quantum theory, that is something which is still a mystery. The ideas, but we've no idea which are correct or whether we could understand them. So I would say that to understand those sorts of things would be one of the challenges, which may or may not be within the capacity of human beings and their intellects. And of course, at the other end of complexity, it's to understand the human brain. I mean, it could be that the human brain is so complicated it can never understand itself. That's a possibility. So there are certainly challenges at every level in science, and they stem from when the mysteries are part of physics, as it were, to the other extreme when they're part of biology or psychology. But there are these frontiers, and the thing about science is it's an unending quest, and as the frontiers advance, their periphery gets longer, so that the range of uncertainties and new questions is getting ever larger. And we talked about cosmology, and if I think back to when I was a student in the 1960s, the questions that we were posing then have in many cases been settled, but the questions we are addressing now couldn't even have been posed back then. And that's the nature of science, that we settle some things, but that opens up new questions we couldn't have posed before.
And we have to expect the horizons always to recede, which is a good thing because it means that we'll never get bored. Lord Martin, I want to thank you so much for being so generous with your time and for your dedication to science communication as well, which helped to inspire many people, including me, to study physics. So thank you.
Well, thank you very much for the chat. I must enjoy talking with you. Thank you.
I just want to add here that even after the interview was finished, Lord Rees was still happy to send me some of his recent papers and articles over email, and we'll probably do a bonus episode at some point covering some of the themes that are brought out in those articles as well. I wanted to mention it simply to say that getting to do this interview was a real honour, and although Lord Rees's reputation for kindness did precede him, it was so lovely to get to have a conversation with someone who has dedicated their life both to science and to the communication of science, and the intersections between scientists and policy and all this sort of thing. And I really hope that you enjoyed listening to the interview half as much as I enjoyed getting to conduct it. We will return soon with more episodes. In the meantime, Lord Rees is a new user of Twitter, where he has mainly assembled his new articles and interviews that he's contributed to lately. You can find him at Lord Martin Rees, and you will find many more of his talks and interviews there. I would also strongly recommend Just Six Numbers and Our Cosmic Habitat for this incredibly concise yet wonderfully detailed and well-explained history of cosmology, the fine-tuning problem, and also his book On the Future, which is his most recent book, for some of his work on existential risks and his theorizations about post-humanity and all this sort of thing. There are a few writers with a clearer and more unique voice who manage to pack so much detail and insight into something that's still very readable and comprehensible. And fewer still, of course, who was actually involved at the forefront of a lot of these discoveries. So I highly recommend these books if you're looking for some New Year reading. You've been listening to Physical Attraction. You can find us on the web at physicspodcast.com, and please direct any comments, questions or concerns you may have to the contact form there. I try to respond to all of the emails that I can get hold of. You will also find there the About section, which will tell you the full list of episodes that we've done so far. It'll summarise all the different series we've done on everything from Newton, Stalin and the Scientist, the birth of stars, the end of the world, all that sort of thing. So if you are looking for which episode to listen to next, that would be a good place to go to start and find out what we've covered so far. You will also find ways to support the show via Patreon or PayPal. This is a solo effort, and all of your help is greatly appreciated. Many thanks to the listeners and the Patreons who have contributed already. Until next time then, on the cusp of a new year, please do take care.